Welcome back to Computer Lessons.
We have successfully built a machine that can think, remember, and display beautiful images, effectively creating a digital brain in a jar. However, this supercomputer is currently an isolated genius, completely cut off from the outside world because it has no way to receive commands. Today, we are going to explore the bridge between your biological thoughts and the machine's digital execution, input devices. When you type an essay or aim a weapon in a video game, you probably don't think about the complex electrical engineering happening under your fingertips. You press a key and a letter appears, but the journey of that signal involves physics, matrix logic, and incredible speed. Let's start with the weapon of choice for writers and gamers alike, the keyboard. At its most basic level, a keyboard is just a massive circuit board filled with switches. For the vast majority of cheap office keyboards, the technology used is called membrane. These use three thin plastic sheets layered like a sandwich. The top and bottom layers have conductive traces, and the middle layer has holes. When you press a key, you push a rubber dome down through the hole, mashing the top and bottom sheets together to complete the electrical circuit. It is cheap, quiet, and resistant to coffee spills, but it feels mushy and inconsistent. This lack of precision is why enthusiasts and professionals turn to mechanical keyboards. In a mechanical keyboard, every single key has its own self-contained physical switch mechanism. Under the plastic keycap, there is a stem, a spring, and two gold-plated metal contacts. When you press the key, the stem physically moves down, and the metal contacts snap together, sending a clean, precise signal. These switches come in different flavors defined by their color, usually blue, red, or brown. Blue switches have a click jacket that makes a loud noise and provides a tactile bump, letting you feel exactly when the circuit connects. Red switches are linear, meaning they travel straight down smoothly without any bump or click, making them faster for gaming. But how does the computer know which of the 104 keys you just pressed? It doesn't have 104 separate wires running to the processor, as that would be a nightmare of cabling. Instead, keyboards use a matrix circuit, which is a grid of wires arranged in rows and columns. The keyboard controller, a tiny chip inside the board, rapidly scans this grid thousands of times per second. It sends electricity down row 1 and checks to see if any columns light up, then it checks row 2, and so on. When you press the letter H, you are connecting, for example, row 3 and column 6, and the controller looks up those coordinates to identify the key. This matrix design leads to a common problem in cheap keyboards known as ghosting. If you press 3 specific keys at the same time that share a row and column, the electricity can flow backward through the circuit. The controller gets confused and registers a 4th key press that you didn't actually touch, a ghost key. To solve this, high-end keyboards use a feature called N-Key Rollover, NKRO. Engineers place a tiny component called a diode next to every single switch on the board. The diode acts like a one-way valve for electricity, preventing the backward flow and allowing you to press every single key simultaneously without error. Now let's move to the extension of your arm, the mouse. The days of the heavy rubber ball collecting dust and hair inside the mechanism are long gone. Modern mice are actually high-speed cameras that track the microscopic imperfections of your desk surface. Inside your mouse is an optical sensor, which consists of a tiny red LED or infrared light and a CMOS camera sensor. The light illuminates the surface, creating shadows in the microscopic texture of your mousepad. The camera takes thousands of pictures of these shadows every single second. A specialized chip called the DSP, or Digital Signal Processor, compares image A to image B. It looks at how the pattern of shadows has shifted and calculates the exact direction and speed of the movement. It essentially performs complex navigation mathematics constantly, translating physical distance into digital coordinates. This brings us to the most marketed and misunderstood number in mice, DPI, or dots per inch. Marketing teams want you to believe that 20,000 DPI makes you a better gamer, but that is rarely true. DPI is just a measure of sensitivity. At 20,000 DPI, moving your mouse 1 inch would send the cursor flying across 3 monitors instantly. Most professional gamers actually play at low DPIs, like 400 or 800, to ensure maximum precision and control. What matters more is the sensor's accuracy and its IPS, or inches per second rating. This determines how fast you can physically whip your hand across the desk before the sensor gets confused and spins out. Another critical metric is the polling rate measured in hertz. A standard office mouse has a polling rate of 125 hertz, meaning it reports its position to the computer 125 times per second. A gaming mouse usually runs at 1000 hertz, reporting every single millisecond. This reduces the input lag, which is the delay between your hand moving and the screen reacting. In competitive scenarios, shaving off a few milliseconds can be the difference between winning and losing. However, pushing this too high, like 8000 hertz, can actually burden your CPU as it has to process too many interrupts. We also have to talk about debounce time, a physical limitation of metal switches. When you click a mouse button, the metal contacts don't just touch once. They vibrate or bounce against each other for a few microseconds. Without filtering, the computer would register this as a double or triple click. Software usually ignores these bounces, but as the metal wears out over years, the bouncing gets worse. This is why old mice eventually start double-clicking when you only clicked once. The solution to this mechanical failure is the optical switch, or the Hall effect sensor. Instead of metal contacts touching, optical switches use a beam of light that is broken when you press the button. Hall effect keyboards use magnets and magnetic fields to detect how far a key is pressed. Since there is no physical contact to wear out, these inputs can theoretically last forever and offer adjustable actuation points. Finally, we must address the wireless revolution. For years, gamers avoided wireless mice because of latency and connection drops. But modern 2.4 GHz wireless protocols are now just as fast and sometimes faster than a wired connection. This is very different from Bluetooth, which was designed for power efficiency, not speed. Bluetooth is fine for typing an email, but for precision input, the dedicated 2.4 GHz radio dongle is mandatory. It negotiates a private, high-speed lane for your data, ignoring the interference from other devices. We are still using the QWERTY layout, a design from the 1800s created specifically to slow typists down so mechanical typewriter arms wouldn't jam. It is a testament to how stubborn human muscle memory is. We have surrounded this ancient layout with the most advanced optical and magnetic engineering on the planet. We have covered how the computer thinks, sees, and feels. But a truly immersive experience requires more senses. We need to hear the digital world, and we need it to hear us. In the next video, we will explore digital audio. We will explain how DACS converts zeros and ones into sound waves, and how microphones capture your voice.
Tell me in the comments, are you a fan of the loud, clicky blue switches, or do you prefer the silent, linear red ones? And have you ever experienced the frustration of a mouse that double-clicks on its own? If you found this explanation helpful, please hit the like button and subscribe to Computer Lessons. Don't forget to click the bell icon so you don't miss our next class. Thanks for watching, and keep learning.